Bismillahirrahmanirrahim. Hello everyone, this is Dr. Bassam Alhamad, CHENG324 Process Modeling and Simulation. So today we are starting with lecture number 4. So we're here with lecture number 4. So in lecture number 4, we were, where did we arrive actually? We had the example of the CSTR, and in the example of the CSTR, where we said that CSTR is a continuous input-output, continuously stirred, and this is a tank plus a reaction. And we say that we have reaction, for example, A plus B produces, well, let's say A plus 2B produces C. I think so, yeah, that could be a good example. And we can make it more complicated later if we would like. So it's A plus 2B produces C. Beautiful. So we have an input, we have an output, and we are saying here the input has both A and B inside. So it has a certain concentration of A and B. They are mixed together at a certain temperature with some kind of cooling or heating. And so we will say that with the temperature control, we had a certain temperature, and with that temperature we started getting C. Of course, we have A, B in, and I will say in here, and of course we're going to have A, B out, and C. Well, why do we have A and B out? Because like it's never that we have a totally full reaction that is 100% conversion. So talking about 100% conversion reactors, that like this is like impossible. It never happens. This is impossible. It never happens. So definitely there's some conversion of A and B that is not converted to C, and this is why they appear in the output. Good. So this is what we have. So within this example, we already calculated how to. We said that we want to know how does high change with time. So we have dH by dt, and we said that in this lecture we want to know how does concentration change with time, and that is the first part of this lecture. And then we want to know how does the temperature change with time. Okay, how does temperature change with time? So we do our best now for this lecture for dC by dt, and then we're going to see how does temperature change with time. So recording very quickly from the overall mass balance equation, we already obtained that dH by dt. Well, let me do it again. It's good for practice. So dm by dt is equal to input minus output flow rate. And then we said that m is equal to rho A dH by dt is equal to density into the volumetric flow rate in minus density into volumetric flow rate out. And then we said that density is constant, so we will cancel out the density terms, and we are going to have dH by dt is equal to Fn minus F. That is A dH by dt is equal to Fn minus F. Now that was a mistake that was from the last lecture, but we want to mention that as that we forgot the A term here. So just recalling the A term, so F dH by dt is equal to Fn divided by area minus F divided by area. And then we had F is equal to alpha square root of H, if you just can recall that. And because of this, we are going to have now our equation dH by dt is equal to Fn divided by area minus alpha square root of H divided by area. Okay, so beautiful. So this is what we had from the overall mass balance. Okay, that's really good. Looks great. So let's continue on. Now if you want to find dC by dt, we need to do the component mass balance equation. To do the component mass balance equation, we said that it's better to do the mole balance because it is reflecting more towards what is being reacted and what is being really consumed. So what we are going to do here, we're going to say dN by dt is equal to Nn minus N out. How many moles are left out? And of course we have the generation plus consumption term. The generation plus consumption term. So it's either being generated or consumed. So if it was a reactant, we are talking about it is consumed. And if it was a product, we are talking about that it is produced or generated. So here in this case, what is the consumption term, the generation term? It is the rate of reaction multiplied by the volume. And if you just want to make sure about it, this is moles per liter per second, and this is multiplied by liter. So we have here moles per liter. I think I'll fix up this. So this is like moles per liter second multiplied by liters. So I'm going to have moles per liter. And of course, yes, it is moles per second. And we can see, yes, it is moles per second. So if you just look at dN by dt, here it is moles. Here it is moles. And here it is seconds. Great. So continue on. So dN by t is equal to input minus output plus R A into V. When we said RA, why it is not RB and so on? Because we are talking RA here. A is the limiting reactant. And when we say that the limiting reactant, that means it is going to finish first. So when A reacts with B and produces C. So if A finishes, B has nothing to react with. So because it has nothing to react with, the reaction finishes. It just stops. So the reaction will only go on if we have A. And usually the limiting reactant is the one which is less in amount, so it's going to finish first. Okay, so this is the reason why we're having our A here, and where A is the limiting reactant. And of course here when we say RA, we know that RA for it will be the rate constant multiplied by the concentration, and we are going to go back to this, like if this is true, or it should be minus KCA into CB, or it should be minus KCA into CB square, like, or is it plus or minus, and what's going on with the rate of reaction? We are going to come back to that. As long as we keep it as a rate of reaction now, and we're going to go back, we're going to come back to this equation later. So let's continue just to get the whole idea, and then we're going to substitute for RA. So N, we know that N is equal to concentration multiplied by volume. And here, because we have Na, it's a component mass balance, so this will be dCA V by dt is equal to, that is the molar flow rate. So you're talking about the concentration, and rather than multiplying by volume, it is the volumetric flow rate. Beautiful. Minus, so that's CAN, so this minus CA into F plus RA into V. That's great. So let's continue. So this is the product rule. We are going to apply the product rule here. Both of them are changing with time. So V dCA by dt plus CA into dV by dt is equal to CAN Fn minus CAF plus RA into V. Great. Now, we already have the term of dCA by dt, which is beautiful. But what about dV by dt? So dV by dt, it comes from the overall mass balance equation. And if we go back to the overall mass balance equation, where is dV by dt? Okay, where is dV by dt? So I think so we can get it from here. So before cancelling out the rho terms, so it looks like that. It looks like rho into dV by dt is equal to rho n Fn minus rho F And if you cancel out the raw terms, you're going to have a very beautiful term where dV by dt is equal to Fn minus F. And if you just look at it, that is exactly how volume will change with time. So how does volume change with time? It depends on the volumetric flow rate and the volumetric flow rate out. So if you have more volume in, you have more volume accumulating. You have more volume accumulating here. And if you have more volume going out, you'll have this volume going down. So it just makes sense. dV by dt is equal to Fn minus F. Okay, so I'm going to substitute here. So this is going to be VdCA by dt plus Ca into Fn minus F. So here I'm substituting. Okay, is equal to Can minus, okay, sorry, I forgot something. Can into Fn minus Ca into F plus Ra into V. Beautiful. Now I have only dCA by dt sitting by itself. It is really beautiful. And here, if you can see that we can even simplify this equation more. Why? Because I'm having here CAFN and CAF, and I have here CANFN and CAF. So I'm going to have some common factors and some terms that will be cancelled out. So let's go step by step. So this is like VdCA by dt plus Ca into Fn minus Ca into F is equal to Can Fn minus Ca into F plus Ra into V. Okay, so here if I just can see, this is Ca into F, Ca into F, both of them negative, take it to the other side, it will cancel out both these terms. What about the other term? This term and this term, we have Fn as a common factor, but Can and Ca, they are different, so we're going to have a common factor into Can minus Ca. So the equation will be reduced to VdCA by dt is equal to Fn as a common factor into Can minus Ca that had been coming from this side to the other side, plus Ra into V, and you just divide by V, so you have your equation dCA by dt is equal to Fn over V into Can minus Ca plus Ra. A very nice equation that we have achieved, and if you just look at it, that is just exactly an equation. That is just exactly if you want to find how concentration of B changes with time, you will just do that. And this is the beauty of modeling, because we have the same equations and it will obey exactly the equation. So dC by dt is equal to Fn over V into how much C gets in and how much C leaves out plus RC. Now of course we know that there's no Cn, so this is going to be 0. Beautiful. So these are the equations that we have. And it looks perfect. So how many equations actually do we have? We have like one equation for the height. So we had one equation for the height, dH by dt, and now the equations for the concentrations. We have one equation here, which is number 2, and there's another equation, is number 4, and there's another equation which is number 3 and number 4. So these are the equations that we have for the concentrations. And actually, if you run the degree of freedom, and I'm going to run the degree of freedom, even though that I know that I'm not going to get it as 0, but it's beautiful to do this equation before I get to my final solution. So talking about the degree of freedom is number of equations minus number of unknowns. Yep, we know that, but we want to do the VIP thing. So this is the VIP, and the V tells me about the state variables and the normal variables. What are the state variables? I'm having the height, and I do have CA and CB and CC. Of course, the state variables are the differential equation, So I can see the differential equations here, the differential terms. This is why I have kept them as state variables. And about the normal variables, we can we already substitute for f is equal to f alpha square root of h. So we have here. So just not to forget, the normal variable we already substituted, so we will not include it in the NV. We are not going to include it because it does not appear in any of our equations. There's no f here, there's no f in the third equation, there's no f in the fourth equation, and if you go to our first equation, that is number 1, there's also no f here. Okay, so you don't have f in anywhere else. Okay, but actually normal variables, we have variables. We have other variables. Okay, we have RA and RB and RC. Okay, wow. So we have more variables here. Okay, so let's go to the input. So what are the inputs? The inputs is Fi, and it is CAI and CBI. And we already said CCI is equal to 0, so we are not going to include it in the equation because it will not appear. What about the parameters, the constant values? Well, the constant value, we have the constant values, V here, which is equal to area and to height. And actually, we cannot keep it just like that, sitting here. If Fi over V, if you substitute area and to height, that will be like another normal variable equation. So we say that V is a normal variable equation, and we're going to have one more equation, which is variable is equal to area to height, and that is we already had added. So we have 5 equations in this sense. What are the parameters? The parameters, we have some constant values. If we just can recall, we had alpha. I think we had alpha in that equation. Okay, so we have alpha and the area. Alpha and the area, because we forgot the area in our last lecture, so we do have area here. Okay, so we have alpha and area. So these are the equations that I have. So how many variables I have? 1, 2, 3, 4, 5, 6, 7, 8. Oh my god, I have 8. So if I do my degree of freedom is equal to 8 variables minus number of equations. Oh, I have 5 equations only. So if you can see that it is 3, so it's underspecified. It's underspecified. And if it's underspecified, that means we need to do something. Okay, we need to specify. And actually the specification here is for these 3 terms that we intentionally left them behind. So if we have an equation for RA and we have an equation for RB and we have an equation for RC, then we are going to have 8 equations, and that will be 8. This will be 8 minus 8 equal to 0. Okay, so to complete our 3 next equations, if you can recall, so the equation was, I'll write that in black. So the equation was A plus 2B produces C. Okay, and how do we write our reactions? Okay, so what is the information? The information given in the test, for example, I need to tell you something about it. If I say elementary, definitely the elementary, that means is going to take the equation to the power of the stoichiometric power to the stoichiometric ratio. That is if I say elementary. But if I specify and then I say no, it is first order in A, B, and C. That means I'm identifying that is first order. And in most cases, like just to make things simpler, I usually go straightforward with this one because I wanted to concentrate more on the modeling equation rather than going through the kinetic part of it. Okay, so this is one part of it. Just and to recall something as well. Well, this is the information given. This is the information given for you. Okay, so what do you need to remember from previous things? That if we have a reactant, then we are going to have a negative value because it's going to be consumed, as we said. And if it's consumed, then it's going to be negative. That means the concentration is going to be less. And if we have a product, the product, that means it's just generated. And if it's generated, it will be positive. Well, recalling all the details of what I have mentioned here, I'm going to write my equation. So I have here the rate of reaction is equal to K into Ca into Cb. So that is the rate of reaction. Considering what? Considering that I'm talking about its first order in A, B, and C. And of course, if it's elementary, I'm going to say Kca to Cb square. But I'm not going to say that now. So it's first order in A, B, and C. So the rate of reaction is K into Ca into Cb. Well, if you go now to Ra, I'll write that in blue. I'm just enjoying the different colors that I have. So Ra is equal to a reactant, so it will be minus R, okay, which is minus Kca into Cb. And Rb is minus 2R, so I'm multiplying here by the stoichiometric ratio, and that will be minus 2K into Ca into Cb. And Rc is equal to 1, the stoichiometric ratio, into R, so it's plus because it's a product, and that will be plus K into Ca into Cb. And beautiful. So these are the three equations that I have here, and by adding these three equations, I don't have any other more variables, so it's all Ca and Cb. So I'm going to have in this degree of freedom, I'm going to have nothing's changing other than I'm going to say here that rather than saying that this is 5, now I have three more equations, and that will be 8 minus 8 is equal to 0. And these are the equations that we have for the system here. These are the equations that we have for the system here, and if you can look at it, I'll just zoom out just to get the overall picture. So yep, we started from here. We started from this lecture number 4, where we said that we have for this system, we wanted to know how does high change with time, and we found how high changes with time. And we wanted to know how concentration changes with time, and we found how dCA by dt and dCb by dt and dCc by dt, how do they change with time. Beautiful. But we did not find how temperature change with time, how the temperature changes with time. Actually, I just remember that we have one more constant or a variable. It depends on how the information is given. And there is actually one more parameter appearing here, and this parameter which appears is K. We forgot about K. So we need to say that this is a parameter. Well, K is a parameter. We only can say that K is a parameter. In other words, that I'm saying that K is constant if, I'm saying here again, if temperature is constant. Well, we know that temperature is not constant. So definitely K cannot be a parameter. So if there's an information given within the problem saying that instead of saying that temperature is constant, if it says that's constant, or it says that it is controlled. It is controlled. So what I'm trying to say that here, you're sitting within a room, whatever, you're sitting in a room or watching TV very happily, and within this TV here you have an air conditioner, mashallah, a very good AC, and it has a thermostat, where usually for boys, okay, so they have this air conditioner. Sorry, what happened here? Okay, I think I need to zoom in again. I missed my example. Okay, this is life. We are learning. Okay, beautiful. I'm getting here. I'm really getting very close here. Okay, beautiful. So I have an air conditioner, and with that air conditioner, the thermostat, as I said for boys, they always keep it till 16 degrees centigrade. Freezing. They like it. I don't know why, but they just like it. Okay, so within that 16 degrees, and we have snow coming out. We have snow coming out of that air conditioner, and is he really very happy, and even the blankets is thrown out. Usually it's never on the bed, this is thrown out on the ground, However, let's go back to our example. So what I'm trying to say here is that you have a thermostat here. You have a thermostat. And this thermostat, make sure that the temperature always stays at 16. So when it goes to 17, degrees, then the compressor is off. And when it goes to 15 degrees, which means colder, when it goes to 17 degrees, the compressor is on so that it cools down. And when it goes to 15 degrees, the compressor is off so that it can be, so that it stops cooling. And then we go back to 16 degrees. So this is like controlled. The temperature is around 16, it's always around 16. So what I'm trying to say here, in our simple example here, we are trying to say that now for K, it's a parameter if temperature is constant, or we can say in the problem that it is controlled. That means it does not change with time. And why is all that? If you just can recall the K is equal to K naught into e to the power minus the activation energy over RT. Or sometimes instead of K naught, you say Arrhenius equation is equal to e to the power minus RT. Activation energy is constant, R is constant. Temperature, if we say it is constant, then definitely K will be constant. Okay, so K we added here, we added it here as a parameter, considering that temperature is constant. In our next example, as we are trying to find dt by dt, so temperature will not be constant. So happily for this equation we found dH by dt. So in this problem we have found dH by dt. We have found all the concentrations, how do they change with time, very happily. So what's left for us? dt by dt. So that will be the next example. Inshallah, we'll see you with happy faces. I hope that's not getting more complicated, but believe me, I'm already halfway through or more to the complicated part of the modeling simulation course. It will be much easier in the coming days, much easier. So keep it up, keep yourself with all enthusiasm. That's going to be better, and I hopefully you like this happy face. All the best. I think it became scary. Okay, I'll stop that. See you. Ma'as salama.